Okay, I'm going to look at practice problem number 1 on page 212, chapter 6. Okay, so this problem is you have a boulder, you push it off a 50-meter high cliff, and you want to determine what the velocity is just before it strikes the ground. Okay, and they actually give you the solution here, but we'll go the answers here. That is, but we'll go through and work on the solution for this one. Okay, for this, so this problem, if we just think about it a little bit, um, so what do you have? You have a boulder has some potential energy associated with it, so it has energy essentially stored in the gravitational field, um, and it has, and after you push it off, it of course it starts to fall. As it falls, it accelerates and gets to a certain velocity just before it hits the ground. Well, this one actually follows or fits a type of problem where it's going to follow the uh, first law of thermodynamics, which states that energy cannot be created or destroyed. It can only be converted from one form to another. So initially, we start off with some potential energy by having it off the ground, off, and we say 50-meter high, meaning reference to some point. Um, and it has no velocity associated with it. So it has potential energy, but no kinetic energy. That's where we start off with. And then as it falls, as the rock boulder falls, what happens is that it gets closer to the ground, so its potential energy is decreasing, but its velocity is increasing. So its kinetic energy is increasing. Okay? So what we're going to see is we're going to have some initial energy on the left-hand side of an equation, and we're going to make that equivalent to essentially its final energy. Okay, and those two must be the same, must be equal. Okay, okay. So here we are with the problem. We have initially we're looking for v2. I'll define v1 as like our initial velocity, and v2 as our final velocity, or the velocity we care about determining. Um, so we have a boulder, and that's 700 kilograms. So that has a certain mass. I'll say mb will be the mass of that boulder, and then I'll just write h is the height, or the height of our cliff. Okay. So that's what's given. All right, then the equations. So we're going to follow the first law of thermodynamics, which essentially says, when your initial energy must equal your final energy. Okay, the only thing that's going to happen during this process is it's going to convert from one form to another. Now we have whatever kinetic energy of motion of the boulder plus its potential energy, which in this case potential energy is having it lifted off the ground, is equal to whatever kinetic energy it has in the end, or the second point, and whatever potential energy. Those two added together must be equal. And it must be equal through this entire process. So as it's falling, what's happening is, so you're starting off with no kinetic energy because there's no velocity associated with the boulder initially. And you have some potential energy. But as it falls, what happens is that its kinetic energy is going up and its potential energy is going down. Okay? So as that's occurring, that's the process. So eventually, just before it hits the ground, this becomes zero, and you're left with just the kinetic energy. Okay? So, and just in terms of how you determine the potential energy, it's just going to be the mass times gravity times the height. And the kinetic energy is just 1/2 mv squared. Okay, and this is what we had covered previously earlier in the chapter. Okay, so what we do is we start off with the equation 2, which just, equation 1 essentially is, this is the details behind equation 1. Equation 2, and what we recognize is there's no initial kinetic energy, there's just potential energy at the beginning. And then at the end, or the second point, or just before it hits the ground, there's no potential energy, it's just kinetic energy. So we write out the potential energy on one side and the kinetic energy on the other side. And what we recognize here is that the mass cancels out. Okay, which is an interesting result because essentially it says is whatever you drop will have the same final velocity, right? The only thing that changes really is that wind resistance. Wind resistance could impact that, right? It could make it fall slower. So in our case, the boulder, we say, well, the wind resistance is relatively small, so we neglect it. We don't worry about that in our equation. So we just have basically this and this, okay? All right, so we equate these two, cancel out mass, and then we can solve for V2. And we go through and plug in with the numbers, we come up with 31.3 meters per second for this problem. And that's it.